There was an interpolation property which says the periodic L function at 1 and when I have E over Q elliptic curve with the P split multiplicative reduction, this factor is 0. So LPF comma 1 is 0. Mazur-Tate-Teitelbaum. What can you say about the first derivative? An exceptional zero conjecture, it says the first derivative nothing but the LP invariant times the algebraic factor. This is defined by, I have to quotient out the transcendental factor omega real period of E, and this is defined by this is the exceptional zero conjecture. And there are two proofs, known proofs, and one proof I try to prove by computing the derivative in two directions yesterday by constructing or showing the properties of the periodic function. So that is one proof, and today second proof by Kobayashi. By using the Coleman map and Kato element. Recall the map. This I denoted by delta, and this one is isomorphic to ZP, that I denoted gamma, delta and gamma. And yes, U infinity. This is Kn is a fixed field corresponding to the field extension here, and maximal ideal of OKN. And consider the logarithm map. This is given by the power series. I will follow the yesterday's notation. I will write simply L of x because yesterday I defined L of x. So this L of x, the logarithm map, this is defined by log of 1 plus x. And I defined one more map. This is the formal group with logarithm L. And there is an isomorphism between and that is given by N. These all stuffs from yesterday's lecture, and you can check by Honda's theory. This is really a power series over ZP and all. This is a group law with respect to the formal group here. And this element, this is fixed by the group here, this group delta. So you can consider this Cn as an element of okay. ZP? Is this one? So your question is whether this is really in ZP of X. Yeah, this is, once you know L of X lying inside ZP, direct computation shows this coefficients in ZP of X. Whatever I write here, if anything is not clear, I would suggest to look at Samir's thesis. He wrote a thesis exactly my lecture today. 1 hour lecture, he wrote a thesis and he checked each and every detail in one section. So every statement I write is one section of is one lemma proposition. So. Okay, then I by Tate's periodic uniformization thing, I wrote map phi where Cp is the algebraic closure of Qp. Qp is complete and it's not algebraically closed. Algebraically closed algebraic closure is denoted by Cp. And I defined the Tate curve yesterday. What is EQ? It's given by the coefficients are power series expansion. And when you have an elliptic curve over Q with P split multiplicative reduction, you can think of it as a elliptic curve, Tate curve. There is an kind of, it's a big deep theorem. Or I can give you reference later. So E is, you can think of as a Tate curve with this one. This element Dn, this is 1 plus, this is defined as 1 plus Cn. And by Hilbert's theorem 90, so the element is Xn, and This is by Hilbert's theorem 90, and where this is a generator, fixed generator of gamma. Norm of xn, if you compute, that is p to the power en, that I will use it later. CP, I'm taking QP bar. QP bar? QP bar itself is not complete. Again, you complete it, yes. Okay, yeah, thank you. Oh, yes, thank you. Completion of. Thank you. So this one again, it's a small lemma, and you can refer to Sami's thesis. So these two things, I'm not deriving now. I'm leaving it as an exercise, small exercise, exercise. Just you use the definition of the isomorphism K and the generator comma. This one we saw in Sudhanshu's lecture and all, the same cup product thing. Taking. By Kumar map, we can think the element in here as an element inside the cohomology group, and the Coleman map is defined by some overall elements in gamma n. Here I am using one more isomorphism. So I have the map phi here, and the induced map that gives an isomorphism from the multiplicative things here, formal groups, isomorphism of formal group, and explicitly we can write what is that map. And I'm using here the element Cn, which is inside, if you notice, that is inside Cn. Cn is lying here, but once I have the induced isomorphism, phi cap, I can think of as Cn inside here, okay, using the isomorphism. So Cn I can think Cn element of here, okay. Because the Cn is norm-compatible system, this respects the Galois axiom, this map. And I have a commutative diagram. This diagram commutes. When you have two groups G and G prime, and G prime is a subgroup of G, there is a restriction map, and then reverse direction, if it is a finite index subgroup, then there is a co-restriction map. That map I am denoting here, co-restriction map, okay. So this diagram commutes. When you take limit, that is the Coleman map. Define the projective limit. If you take the Coleman map is defined by when you take limit of this map, then you get a Coleman map. Because of this commutative diagram, you get a map here. Set the tangent space. Tan defines the tangent space of E over K. Then you have the Lie group exponential map. Dual map. This Coleman map can be written in terms of the dual map, dual exponential map, as explicitly trace of kn over qq and logarithm of the formal logarithm group. Then I can write omega e. Formal group. Let Gn be the Galois group, the nth layer. Consider a finite order character. There exists a Kato element. is 1, if chi is a non-trivial character, and this is 1 minus 1 over p if chi is real. This is one of the result of Kato. The periodic L function that can be realized as an element of reversal algebra evaluated at a point. I will use these results in my proof. I stated it here. I am not going to give any proof or anything for that one. This is a property, again you have to verify by using the element dn 1 plus cn, substitute and evaluate. These three things, take it as a statement and then we will use it in the proof. Can you see here or erase and write it there? You can see, okay. So now consider the Coleman map. This is defined as all element varying over gamma n. By 1 and 2, you can write the Coleman map evaluated at the Kato element, applied chi. So you have the, when you take z as z Kato, you have the right hand side, the algebraic part, and that comes here when you evaluate. Here when you sum up a log, when chi is non-trivial, you get the Gauss sum that appears here when chi is non-trivial. So you have another element in the reversal algebra that gives you the same right hand side. Because we know the property when a power series ring, if you have it, can have only finitely many zero. So from this statement, from here, this is true for all non-trivial chi. This implies your Coleman map evaluated at Z Kato. So I want to compute the derivative at 0.0. In this statement, I will explain what is phi and what is cup product with respect to GM. You know what is cup product with respect to E, that is a definition of the Coleman map. You know cup product with respect to E. Then I will explain what is this element phi and with respect to GM. Basically, I am using the isomorphism phi cap, that's all. So the E to GM, that will be transferred as the original in non-degenerate pairing, that will be transferred to the following. Here pi is the map. So here, instead of Cn, you will get Dn 1 plus Cn, and En this Z that is like pi of Z because of this dual map that is coming from the isomorphism between E and G. Okay. When you go mod gamma n, because of the definition, that is nth map. Now I want to substitute that Hilbert's theorem 90 and write this Dn as gamma of xn by xn. Use the linearity property, and I am getting the generator 1 over inverse time minus 1, and that product. This is isomorphic to almost 1 plus x. The lower isomorphism, this is mod gamma n. Now denote Cn of x, image of Zp of x minus 1 and C of x So I want to replace gamma by 1 plus x, and I want to think it an element of Zp of x. That's what I'm going to do now. So this C of x, here I substitute instead of gamma, I substitute 1 plus x. Minus 1 and take the limit as x tends to 0. Here mod p2 power n. Here I am using the congruence relation which I wrote, my beginning of talk I wrote En is congruent to minus p by p minus 1 log times the topological generator. This congruence you have to verify. So this is true for all mod p to the power n. So when you take n tend to infinity, you will get this one. So I proved this result. When you take the derivative, this n tend to infinity, then you will get p comma phi. Mhm. Here. Mhm. Mhm. Thank you. Here. Okay. Thank you. So for proving that, I considered mod p to power n. I used the nth Coleman map, and I could get that result. We have the split exact sequence, and take the dual. So this is the commutative diagram we have, and I want to show you the element 1 here. If you take the element 1, then that goes to QE tensor 1. That you can see from this isomorphism also, QP cross tensor with ZP and ZPs. You taking an element 1 here, it goes to QE tensor 1. maybe. If you take an element in T star of 1 and I apply pi and I get an element W, suppose W is this form. Because order of P of P is 0, you can replace this by order of know the derivative at 0 of the Coleman map. I know the power series evaluated at x equals k to power gamma raised to power s minus 1 is nothing but the periodic function. So if I substitute instead of z Carto element, then I get the LP invariant factor, and because this factor 1 minus 1 over p, which comes from the exponential thing, that will cancel with this term. This term p by p minus 1, that will get cancelled with this term 1 minus 1 by p, and this factor, this is coming because of the change of variable. This factor, it is because of the change of variable. Again, there are some gaps. I assumed some statements without deriving. Those are easy if you apply the right definitions and all, because I want to complete in 51 hours. So you can refer to Samir's thesis. He wrote and he checked each and every statement, whatever I wrote today.